Hey y'all, it's your personal math teacher, Mr. Boyden, back at it again, and we're going to continue today with density curves and an introduction to normal distributions. So you can see there are our four things here on the screen we're going to talk about today: density curves, normal distributions in the normal curve, the empirical rule, and the standard normal distribution. So let's get right to it. What is a density curve? A density curve is just some curve, and it's going to be on a graph typically is where we're going to see it. That is on or above the horizontal axis and has an area of exactly 1 underneath it. Now that exactly 1, it's stemming from 100%. Okay, it's got a total up to 100%. And in this case, it's an area. If you've taken calculus, it's basically an integral. Okay. And the reason it's above the axis is because it's kind of sort of represents probability, and we know there's no such thing as a negative probability. Okay, so an example of a density curve is right here, the distribution of household wealth in America. And if we filled in this entire area, it would need to come out to be 1. Let's look at a simple example to get a little bit more of a clear picture of this. And here it is. 2 dice are thrown and the sum is observed. We're going to sketch the distribution of relative frequencies. Remember, relative frequencies is like a proportion or a percentage of each outcome, and we're going to sketch that density curve. So here we go. An easy way to think about that, if you throw 2 dice, the outcomes range from 2 to 12. Let's record those possible outcomes in a table. In fact, almost any time you're dealing with a dice problem and you need probabilities, this is usually an easy way to think about it. The first die is going to be a 1, 2, 3, a 4, a 5, or a 6, assuming it's a standard die. Second die, same thing. It's going to land on a 1, 2, 3, 4, 5, or a 6. And then we're just going to fill in this table with all the sums. So like, for example, this is saying if you have a 1 and a 1, that's a sum of 2. A 1 and a 2, that's a sum of 3, and so on. So let's finish filling this out. Ta-da! So there's our complete table. And we can see here that the smallest value in the table is a 2, and the largest is a 12, and that makes sense. We said the values would range from 2 to 12. So now we're going to sketch the density curve, or the density function. Okay, so our possible outcomes were 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I'm going to label that this is the sum observed down here. And then over here, we're going to have our relative frequency. And so what's the most frequent one? Looks like getting a 7 is the most frequent. So 1, 2, 3, 4, 5, 6. That's 6 out of 36 outcomes. So I'm just going to go 1, 2, 3, 4, 5, 6. And we'll have this represent 6 out of 36. I'll label this one as 3 out of 36. And now let's sketch that distribution. So we start, 2 occurs 1 out of 36 times. So there's the bar for 1. Fill it in if you want to. 3 occurs twice. 4 occurs 3 times. 5 occurs 4 times. 6 occurs 5 times. 7 occurs 6 times. And so on. I'm going to sketch the rest of the distribution out here. Now, quick question. If I were to add up the areas of all of these rectangles, what would that total area be? So like all of this total area, whatever you want to call this shape, what would that be? Don't actually calculate it. In fact, I hope you've already come up with the answer. The area has to be 1 because it's all of the possible outcomes. Each one has its own probability, and all of the outcomes in the sample space have to add up, or their probabilities have to add up to 1. So that area is 1. So guys, just a simple example here, okay? Just with dice showing this is an example of a really basic density curve. Before we keep going too far, I do want to add this note. The mean of any density curve is sort of the balance point. That's if like you made it out of wood or out of foam or something, it would be the point where it balances. So we have that shown right here. And I'm going to call that X bar. That's what we've called it. The median is the point where 50% of the area is on the left and 50% on the right, because medians where 50% of the data fall on the left, 50% fall on the right of that point. So quick question. On this bottom image, I'm talking about this one right here, approximately, where is the median? Maybe pause the video and think about that for a second. The median has to be to the left of the mean. The median is somewhere in here. We don't know exactly, but how do we know that? Well, this is a right skew, and in a right skew, the mean is going to be dragged to the right because it is less resistant, reviewing from a few lessons ago. Okay, so the median had to be on the left there. All right, here's another one to think about. I would like you to pause the video and try to answer this one for yourself and then hit play to get the explanation. Identify the mean, median, and mode in the following density curve. All right, guys, the mode is here. Remember, mode means occurring most frequently, and the density is kind of like the relative frequency. So the one that's most frequent is the mode. This is a right skew. And I know there's this little teeny tail down here, but look how big this big swooping tail is. That's a right skew, which means the mean is going to be dragged further right. So this is the mean, and this would have to be the median. Here's another example. In this one, we're not given a visual. Consider a density curve defined by the endpoints 0, 0, and 4, 0.5. Sketch the curve. All right, let's do that. Now, I realize that it's not super explicit here, but it is my intention with this question that the curve is defined by a line segment or a straight line. So that's what I'm going to show here. So I'm just going to call that 0.5 on the y-axis, and we'll go 1, 2, 3, 4 on the x-axis. So that's the 0.4, 0.5 right there. And we have 0, 0 down here. Let's play a little game of connect the old dots. And there is our curve. Hey, quick question for you. I just drew a triangle. What's the area of that triangle? And don't calculate it. Just tell me, what is the area? Guys, you should know that the area is 1. It is a density curve. The area of the region under, so I'm going to say region under, I mean like this. The region under any density curve needs to be 1. So you don't need to calculate it. You should be able to just say it. Okay? So part A is done. Let's go to part B. What percentage of the values will fall between 0 and 2? All right, 0, so 2 is right here. 0 and 2 is this shaded area. So what this means is the percentage of values that fall there is the same as the area of that triangle. So here's our work for part B. Remember that the area of a triangle is base times height divided by 2. So what's the base? 0 to 2 is a base of 2. What's the height? Okay, well, it's halfway there, so that's 0.25. Height is 0.25. And so base times height divided by 2, cancel the 2's, and that's 0.25. It asks what percentage? 25% of the values fall there. All right, then we're asked to estimate the mean and the median of the distribution and to determine if it's possible to find an exact value for either one of them. The mean is a little bit tricky to nail down. There is a way to do it, but we're not going to show it here today because it's a little bit advanced. I am going to show how to find the median though. Here's what we would think about. There's some spot in this triangle such that 50% of the area, or an area of 0.5, lies on the left and an area of 0.5 lies on the right. And so if you look on the left over here, I'll highlight the triangle that we'll focus on. So there's a triangle over here, which has some base, which we'll call, well, let's call it x because it's going on the x-axis. And it has some height that's related to the base. And we're going to try to figure out what triangle has that area of 0.5. So part C, here we go. The way I'm going to approach this is when I go to set up my equation for base times height divided by 2, instead of base, I'm going to put x. I labeled that already. And I could write h, and I'm going to put it over 2. I'm not going to write h yet. I'll show you why in a second. And I want the area to be equal to 0.5. And the issue is, if I put height right there, I'm going to have introduced a second variable into the equation. And I don't really want to introduce an additional variable. That may make things more challenging. What I'm going to do instead is I'm going to try to write the equation of this line. So equation of a line, I'm thinking like y equals mx plus b. The y-intercept is 0. Sweet, that makes that easy. That's gone. Now I need to know the slope. Well, let's look at the rise over the run. The rise, for if I go all the way out to this point, is 0.5 and the run is 4. So that would lead to y equals 0.5 over 4x. I'm going to simplify that so there's no decimals, and I'm going to call it x over 8. So now, whatever the height of this is, it's going to be defined by the equation y equals x over 8. That'll be the height, so I'm going to write x over 8 right here. Let's simplify. This turns into x squared over 16 equals 0.5. Let's multiply both sides by 16, so we get x squared equals 8. Take a square root, and x is equal to 2.83. And so we actually are able to calculate the median. We have to use some algebra tricks, but that's okay. And then the mean, like I said, that's not going to be as easy, although it appears that with this skew, it might be somewhere to the left of that value. All right, now to the normal distribution and the normal curve. So a normal distribution is a symmetric single peak bell-shaped distribution. And the distribution is describing how data are laid out. The normal curve actually is a specific equation. Okay, we're not going to be concerned with the actual details of the equation. Just know that it produces sort of this, what people typically call a bell curve. So things you need to know. The next part, this is for AP only. Okay, and out in the world, I mean, it's not bad to do it normally, but this is for the AP exam. Nothing in the world is technically exactly normal. Okay, so you can't say like, oh, well, the distribution of blood pressure is normal. Can't say that. You have to say that it's approximately normal. Okay, it's more honest, and specifically, AP will take our points away if we say that it's exactly normal, or if we say it's normal. If you don't include the word approximately first, like on a free response question where you could have scored 4 points, now you're out of 3. The best you could possibly do is 3 points. So it's very punitive. It's easy to get right though, so we want to do that. Okay. So down here, this is just a basic picture of the shape. In terms of things that are approximately normal, I just pulled this off of a website with 12,533 data points on Honda Civic from the drivers who drive them, and that appears to be approximately normal. Other things that are approximately normal, things like most blood test results, like almost all of them, your blood pressure, resting heart rate, the height of human beings, standardized test scores like the SAT. Do understand though that when we talk about things that are approximately normal, we're talking about enormous data sets. Okay, like this one has 12,000 data points. That's totally typical. Okay, so we're not saying like, oh, there's 8 data points and it's approximately normal. Nah, that's pretty useless. You need tons and tons of data to be able to get this smooth sort of bell curve shape. All right, so let's talk about the empirical rule. Basically, the empirical rule is a shortcut to answer this question. The question of what percentage of data fall within 1, 2, and 3 standard deviations of the mean on the normal distribution. Now, it doesn't say that, but the empirical rule is always referencing the normal distribution or the normal curve. And so what we're going to do here, let's sketch out each of these, and then we will use the calculator to figure it out, because we're not going to do that by hand. So, and my sketches are really rough, but here they are. So here's my first, here's my second, and here's my third. And here's what we mean by this. The mean is always in the center. Okay, so the mean is the center of the distribution. Let me mark that. And when we say 1 standard deviation away, what we mean is if I come here to x bar plus, and I'm going to use sigma. We sometimes use sigma for standard deviation, sometimes s of x. We'll learn about y later in the course more. And then over here we have x bar minus sigma. So what we're saying is whatever the standard deviation is, it's that distance away. So that's the area we're going to find in a second. Next one, if we did x minus 2 standard deviations, that's 2 standard deviations away on either side, or x bar plus 2 sigma. And then on the third one, oh, let me put the bars in. So that's wider. And then my sketches are not excellent, so it's going to be a little bit hard to tell on here. But if I come down quite a ways, and I call that x bar minus 3 sigma and x bar plus 3 sigma. So now what we're going to do is we're going to go try to figure out what area each of those would have. When I say the area, I mean like we're going to have the calculator right now tell us the area of that, whatever you call that shape. I'm not really sure what I would call it. So let's switch over to the calculator. If you're using a TI Inspire, it actually doesn't matter this time if you just use a calculate screen or if you actually open a document. I think I'm just going to go to the calculate screen, make it easy. And then we're going to get to the normal distribution calculations. Now remember, everything in this calculator that's good, pretty much, happens after you press the menu button. So I'm going to go in there. The normal distribution calculations exist in two places. One of them is in probability. One of them is in statistics. It's the exact same thing. It doesn't matter what you pick. Remember, it's normal distribution, so I'm going to go to probability, then it's the distributions menu, and then I'm going to use Normalcdf. CDF is going to be finding an area. That's specifically what it does. PDF, the one above it, finds an exact value. Now, to be honest with you, I almost never go through these menus. And if your calculator is different than mine, you'll want to find out what the exact button presses are. But on mine, if I hit the menu button and then I press 5, 5, 2, it automatically does Normalcdf. It navigates that menu because it's got those numbers next to it. I think you should figure out what that is and write it down for yours. If you're lucky, it's menu 552, just like mine, and then you won't have to go through this every time. Now, lower bound and upper bound, those are referring to sort of like the x values. The first one we're doing is 1 standard deviation to the left of the mean and 1 standard deviation to the right. So our bounds are going to be -1 and 1. And let's see what we get. All right, 68%. Let's do the calculation again. Menu 552. But this time we're going to find what percentage of the data fall within 2 standard deviations of the mean. So 2 standard deviations to the left and 2 standard deviations to the right. There's my setup. And if you need to pause the video so you can go through the buttons, that would be awesome. Please make sure you take time to hit the buttons so this really sinks into your memory. Okay, here's the next one, 95%. Let's do the last one, menu 552. Now 3 standard deviations to the left and 3 standard deviations to the right. So within 3 standard deviations on either side. And I get 0.997. So these 3 numbers are what we mean when we talk about the empirical rule. We'll see some examples of how to use it in just a minute. Maybe that'll help it make sense. Let's fill those in. So 68%, 95%, and 99.7%. And people, you got to commit that to memory. Okay, I'm going to write that up here. The empirical rule is 68, 95, 99.7. Okay, that's a shortcut to remember how much of our data on a normal distribution fall within 1, 2, and 3 standard deviations of the mean. Let's try then to apply this to solve a question or to answer a question. Okay, here's our first one. And it says no calculator. Here we go. Studies of automobile safety indicate that stopping distances of a given car are approximately normally distributed. For a given model of car, traveling at 62 miles per hour, the stopping distance is, should say is, not in, is, and guys, that is the Greek symbol mu, which stands in for the mean, and that's a sigma, which stands in for standard deviation. So the mean is 155 feet with a standard deviation of 3 feet. And we're asked about what percent of cars of this model would take more than 158 feet to stop. I would like you to draw a picture for that. And I do this every time. It makes it easier for me to think and understand the question. Okay, so there's my normal distribution. I'm going to go to the center of it. I'm not going to put X bar. I'm not going to put mu. I'm actually going to put the number. They told me the mean was 155. And then I'm going to go out to what they asked about. They asked me about 158 feet. So I'm going to draw a line upward, 158 feet. And this is what they want in the question. They want to know what percent, which is analogous to what area is shaded right there. Now, it might not be obvious what to do at first, but let's compare it to what we did a minute ago. Right down here, and I'll mark it in red so it shows up better, this is a distance of 3 feet, yeah? Because it goes from 155 to 158. It is also a distance of 1 standard deviation. And that matches exactly what we did a minute ago right here. It's the mean plus 1 standard deviation. So if I go to the other side, and I go the same distance, 3 feet or 1 standard deviation, to 152, and if I go like this, I know that this area in here is 0.68 because of the empirical rule. And since this graph is symmetrical, this area over here matches this area over here. Well, if 0.68 is on the inside, then the complement of that must be on the outside. That's 32%, which means that there's 16% right here and 16% right there. And this does keep shading all the way out. I didn't mean for it to look like it stops there. So what's our answer? 16%. 16% take more than 158 feet to stop. All right, part B. A car of this model that takes 158 feet to stop is at about what percentile of the distribution? Okay, another way of asking that is, in this distribution, what percentage of the cars have a stopping distance that is a smaller number than 158? Well, we just found out that 16% is what's above. It must be that 84%, the complement, is what's below. Okay, let's try another one. Given that SAT scores are normally distributed, should say approximately, shouldn't it? Haha. What percentage of SAT testers end up with a z-score that is less than -2? Now notice the difference here. We don't know the mean or standard deviation, but we could remember what a z-score means. What this means, a -2 means 2 standard deviations below the mean. All right, let's draw that out. So if I draw the curve we had above, 2 standard deviations below, 2 above, so x bar minus 2 sigma, x bar plus 2 sigma, sigma for standard deviation, we found that the area in between was 95%. And since this is a symmetrical graph, it must be 2.5% down here and 2.5% over here, so we get a total of 100%. So let's read the question again. What proportion of SAT testers end up with a z-score that is less than -2? Well, here they are right here. It's 2.5%. Phew, done. That's it. All right. Number 3, and we're going to be doing 4 examples today. So this is our third of 4. Now we're going to be able to use the calculator. In 2016, more than 1.6 million students took the SAT, and the scores were approximately normally distributed. The mean on the math section was 508, and the standard deviation was 110. So we're going to be plugging that in the calculator here in just a minute. Let's read the questions first. We need to figure out what percentage of students scored less than 350 on the math, about what percentage scored higher than 700, and what percent scored between 400 and 600. What I want to do first, before we go to the calculator, is draw out all of these pictures. So like this, and if the mean, and I didn't mean to make that tail longer than this one, it should be symmetrical, of course, right? So the mean is 508. First question says scored less than 350. So 350, start shading. One thing I want you to notice as I shade is, where does this graph end on the left? Okay, according to your calculator, it actually goes forever. I know that's super weird. We obviously know you can't get a negative SAT score, right? But according to the calculator, it thinks this goes forever. That will inform what we type in here in just a minute. Similarly, on the second one, it says what percentage score higher than 700? If the mean is 508, 700's over here. And so again, as I shade this, how far does that shading go? Technically, it goes forever. And we'll use that in the calculator in just a second. Third one, what percentage score between 400 and 600? And notice these are really rough sketches, but they're going to make it really easy to see what to type in the calculator. 400, 600, that's our shaded area. So now that I have all 3 of those, I'm going to jump over to the calculator. All right, remember to use your shortcuts, menu 552. For the first one, we wanted to know the probability, or what percentage of students scored less than 350. So our lower bound, that -9E999, that's the biggest number really this calculator can handle. It's saying that it goes a long way to the left. The upper bound on our region is 350. Mu, the mean, is 508. And the standard deviation was 110. All right, so 7.5% is what I got out of that. 7.5% of students scored less than 350. Let's do the next one. Next question was asking about what percentage of students scored higher than 700. So if it's higher than 700, 700 is our lower bound. Remember, the normal distribution goes to the right forever. So what I'm going to do is I'm just going to type in a whole mess of 9s. Since we are going to be rounding our answer, a bunch of 9s is close enough. The mean, still got to put it in because we know it. 508, 110, and let's see what percentage of students scored higher than 700. Probably not that many. That seems like that'd be hard to do. Yeah, there it is, 4.0%. All right, and the third question. We're going to figure out what percentage of students scored between 400 and 600. That should be a higher percentage. I think more students score in that range than at the extremes. So 400 on the lower bound, 600 on the upper bound, 508 mean, 110 standard deviation. And yeah, that makes a lot more sense. So 63.5 students, 0.5% of students, scored in that range. Let's answer our last question of the day. The amount of annual rainfall in a certain region is known to be a normally distributed random variable with a mean of 50 inches and a standard deviation of 4 inches. If the rainfall exceeds 57 inches during a year, it leads to floods. Find the probability that during a randomly selected year, there will be floods. Yeah, let's figure it out. So the mean is 50. Draw something bell-shaped in there. It doesn't have to be exact, doesn't really even have to be close, but it has to be good enough. And exceeds 57. That means more than 57. All right, so we're finding this right here. So we're actually, now that we have that picture, we know the mean and standard deviation, we're ready to go to the calculator. All right, back to normal distribution. Menu 552. Mean was 50. Oh, I put it in the wrong spot. Mean was 50. Lower bound was 57, right? So 57. The upper bound, it's boundless, goes forever. And the standard deviation was 4. And let's see what the probability is of getting a flood year. 4%. Okay, so not bad. All right, y'all. That's going to be it for today's video. We'll have more on normal distributions next time. Hopefully you enjoyed it, and we'll see you then.